just going to say that the word help is a little bit ambiguous.
Yeah, actually this whole...
I mean, everybody can jump on me if I'm wrong. This has been a while since I thought about this, but I thought in principle it's possible to use any.
No, because you have to know what the electric field is to solve that surface integral. But if you can exploit some symmetry, then you can take E outside the integral and solve for it. But you could, in principle, calculate the flux through any surface, obviously, if you know what E is already.
In this case, you'd have to know it's a constant already before you start.
No, this is
But it is a constant already because you know it's an infinite sheet.
Yeah. But you don't.
But if you're a student,
figure that out.
You don't know that.
You use this to argue that it's uniform.
The R cancels out after you do the integral.
So you can, I think...
No, I don't think so.
I don't think it's obvious that the E field is constant.
It's an infinite sheet of charge.
So maybe it goes like 1 over R.
You go away from something, the effect.
The field gets weaker, obviously. Yeah.
Students might think that.
Students might. You don't know that until you've done the
You're getting old, no, you forgot what students think.
Okay, this is...
All I'm saying is that
the word help is what
help is ambiguous because
and
it's which of these is possible or which of these would be most useful.
Right, I agree, and it's ambiguous in other places in this multiple choice too, where they put like which of these could you simply calculate.
Yeah.
Right? Instead of which of these could you calculate. But you raised a very interesting point about whether it's possible to do anything with the sphere, which I want to discuss for a minute because it's going to come up later. Because this is an infinite flat sheet, you can decide that the E field only depends on how far away you are from the sheet and that it has to point directly away from the sheet. So that's all you can decide from the symmetry, are those two things. Which mean that the surfaces you want have to be parallel to the sheet for E dot dA to be 1. And also you don't know that the magnitude's the same everywhere on this.
But you know, I don't want to
in terms of sines and cosines.
Right, I don't want to belabor this, but you could actually.
No, if you had already decided that it was constant, right, which it is, the E field's constant, it doesn't decrease as you go away, then you could use the sphere. But you can't. You use this to decide that.
Yeah,
that it's constant.
Right. If you didn't
prove
that
the E field is
prove that it's
constant,
constant
is
using this.
given by Gauss's law.
Yeah, I mean,
or a direct integration.
I don't think you can argue directly from symmetry that it's going to be constant. At least you're not going to convince me. But this is very
Good thing
interesting.
you didn't write this question, Rachel.
But we did in fact use it as a clicker question, which is part of why I brought it here. Brought it up is because we could compare. This is one where we could compare all the students. We did use this as a clicker question in the junior E&M class.
Did you interview students on this question? I mean, do you have any?
No, I want to start doing interviews because I haven't done any interviews specifically on Gauss's law. So I would say that the sphere, it's not possible. It's possible you can use it for the flux, but you can't use it to calculate the E field. Like you know that the charge enclosed, so you can figure out what the total flux is, but you can't pull E out of the integral.
Unless you assume that the E.
Sorry, no. I don't want you to.
Moving on to data.
Derail
The
this.
picture's gone.
Can I have a cookie?
Will you pass the nuts?
So this is the correct answer. The cylinder and the cube, because they have those flat surfaces parallel to the parallel and one distance away from the uniform sheet. So you have what you see is these three columns are from the paper, and those students, the introductory students, on average got 57% got this right. The upper level students, 68% got this right. Then their graduate students, almost all of them got this right. And then when this was asked as a clicker question in the junior level E&M, the 33, 10 to 5, again, nearly everyone got it right.
But that's post-pure instruction.
Right, and that's also sort of in context. Like they just had been discussing Gauss's law in the class. Then they discussed it with each other, then they answered the question. Whereas these ones were all multiple choice tests sometime after the fact. So it's a different context. But it would be interesting to give this multiple choice test to our juniors and see. Now that we know, I'm going to show you evidence that they have problems with Gauss's law. They're not going to score 96% on all the questions afterwards. So it would be interesting to give this to our juniors to see how they compare. This is,
So I'm really not going to push on this anymore after I say this, but if we decided that E was acceptable, then
not.
It's not.
57
It's not.
plus 20.
Sorry. There's
Whatever,
there's
guys.
just no way you
It's-
can compute E
so
using the spherical
Afterwards,
Gaussian
we'll have a
surface.
discussion.
And we'll
that will
explain that
convince you
later.
that E is not a possible
Yeah,
answer.
you explained it, I just- not
Unless you make
convinced.
Noah's assumption.
Let's
Well-
know the answer before you
Right.
start.
If I assume that the E field goes like 1
Okay,
over distance,
let's
then
move
I'll get a
on.
different
Okay.
answer.
Otherwise, we're
So-
gonna. But
But
we're
who's to
invoking
say that the
Minkowski.
students
By the
don't
way, I
understand
didn't-
that?
I didn't say correct, I said an acceptable answer.
Yeah.
But why would
Okay.
it be? Oh.
Okay.
Okay, so
Because-
actually I have another.
It's only unacceptable if you understand the physics and what exactly you're after in this problem.
Well, so maybe this is
Math-
worth talking about. I mean, when you say if
What is making students answer that question? What do they think?
Right.
What do they
Like-
think is correct?
Right.
about
So
this?
I'm gonna tease this out more because we have another similar question where I have some written responses, and it's interesting because I think some students are kind of going in the direction that you're mentioning, and some are going wrong in other ways.
And I have a PhD, so they don't know.
Okay, so here's some of the difficulties in Gauss's law that I observed in 3310. Again, I saw that students were overgeneralizing the results from the highly symmetric charge distributions and just sort of applying Gauss's law all the time. But then some new things, I noticed students were just very imprecise about symmetry arguments. Like they knew they needed to use symmetry arguments in order to use Gauss's law, but they just sort of do it shorthand, like say, well, we're using Gauss's law by symmetry. And then also there was this other idea that in the less symmetric situations, students think it would be difficult and messy, but possible in situations where it would actually be impossible, similar to the situation we were just discussing. And it turns out that this is one I haven't seen before in the literature, and it seems pretty common with our juniors in the course. So the question, yes.
Is that specific to using Gauss's law to calculate the E field, or are they talking about how to do the surface integral?
it's specific to
Yeah.
Gauss's law.
And it's specific to
Using
when you want to
Gauss's law.
calculate the E
To
field.
calculate the E field.
Yeah, it's specific to when you want to get E out of that integral.
Usually
Right,
the
'cause-
math is hard.
Because they have learned how to directly integrate Coulomb's law in this class as well. So they're aware that there is a messy integral that can be used to find the E field. And so part of what I think what Rachel is seeing is that they're confusing the difficulty but possibility of using Coulomb's law with the impossibility of using Gauss's law for a non-symmetric situation.
Wow.
And I'll
Does that
show
make
you
sense?
some.
Yeah, I was just making sure that they're not talking about calculating flux.
Yeah, I don't think they're calculating. I don't think it's. I'm not talking about calculating a flux, and I don't think the students are either.
Okay.
So I'm going to show you some results from a midterm exam question, and this question was asked in the traditional lecture, the one right before the transformation was started, as a midterm question. It was asked in at least 2 transform class, and Steve used it in the paradigms course as a final exam question. So there's lots of answers. So the question is: suppose I evenly fill a cube, and this is just how it is just like it is on the exam, so you can see the exact wording. Suppose I evenly fill a cube length L on a side with electric charges. I then imagine a larger closed cubical surface immediately surrounding this cube, length 2L on a side. Then I ask, is Gauss's law true in this situation? Briefly, why or why not? And can one use Gauss's law to simply compute the value of the electric field at an arbitrary point outside the charge state? So this is again asking about computing the E field, like not about the flux. So it's focused on, can you use Gauss's law to compute the E field? And so most students are pretty happy Gauss's law is true, though there were a few people who aren't. But nearly universally students think Gauss's law is true. So the interesting thing is what they say about can you use Gauss's law in this situation. So there's some students who seem to have it correct with the correct logic. Here's a couple examples. Can we use Gauss's law? It cannot be used to simply calculate the E field because over the outer box, E is not constant, so the integral of E dot j cannot be replaced with EA. So I think that's a pretty complete logic. They're realizing you can't pull it out of the integral and get E separate. Yes?
This does go back to the last question, but in a different way, which is, you seem to be saying that the integral of E dot dA, I mean Gauss's law, the way it's being sort of taught or framed by symmetry, is one where you can assume that E is constant given the symmetry that you haven't pull it out.
Huh?
Well, that's what this argument is arguing for.
I disagree completely. I don't know what you're saying.
Well, I think you don't know what I'm saying, or you disagree
So
completely.
say it again.
I understand what you're saying.
Say
I
it,
disagree
no,
completely.
say it again, because I don't
Say it
understand
again.
what you're saying yet.